the other side. Hi, everyone. Welcome, and thank you, Martin, very much for the invitation to speak here. It's kind of hard to follow this. It was really inspirational, but I'll take you back to Earth, and I've sneakily put in some doom and gloom in there so that our trip to Mars is not a mandatory one, but more of a leisure one. So I'm a researcher with a block research group at ETH Zurich. And what we do is we find methods to design and build more efficiently. And why we do that is because, and here comes the doom and gloom, bear with me, construction is about 40% of all greenhouse gas emissions. By 2050, we'll be more than 9 billion people, and that's a whole lot more people. So it's the whole population of the 1920s added. And that means that if we construct the way we do now with the materials and in the same standards, we'd be going through 60 billion tons of material a year. And if that sounds like a lot, it is because it is a lot. That's kind of constructing a New York every month, a Paris every week. If Trump is more to your liking, then a wall around the equator that is 2 kilometers high and 30 centimeters thick. So we really need to do something about the way we construct things. So, oh, sorry, and that will be quite a lot of waste. So we take our inspirations from structures of the past. So for example, this one, if you look up, you'd think that this is a very heavy structure that has very thick stone, but actually it's a very thin stone vault that is proportionally only as thick as an eggshell. And why this works is because it gains its strength through geometry rather than the amount of material that is used. And that is kind of at the core of everything we do. And it's not because we're trying to design cathedrals again, but because we're trying to take these principles and work with them. So we apply these with using 3 principles. That is using structural geometry, because that means you can use less material. We work a lot with funicular form, so with compression-only structures. That means you can use other materials. It means you can use weaker materials or more sustainable materials that are not the conventional ones. And finally, we also do a lot with digital fabrication, because that means we could have less weight in the construction process itself. And I'll be talking mainly about the first and the last point, and not so much about the funicular form part. And what we do is we build a lot of prototypes to test out these things. Some of these prototypes use weaker materials, so you have mycelium over there, some recycled cardboard in other places. We really look at how you could use materials more efficiently and design it more efficiently. What we also do is share all of this. We do it computationally, and we share all of this in a open source computational framework, which is called Compass. It's based in Python, and that's out there. But what I will be talking about are actually the challenges associated with building complex concrete structures. So, concrete is a great material. We all love it, not because it's the same as the other ones, but because it's really moldable into any shape. And especially for doubly curved geometries, we use it a lot. Now, these geometries, architecturally speaking, we've heard today, could be because we really like something. So it's an architectural expression. But they could also be the result of having structural efficiency or material efficiency, and that's what you can see more on this side. And those are the ones that we are more interested in, but they also have complex geometries, and we need to construct them better. So what these 2 types of geometries have in common, even though they are very different, is the way they are being constructed. And that means that you need a formwork, and that is the same regardless of your geometry. It has stayed unchanged. You have timber. Well, nowadays you have timber or milled foam most of the time, formworks that are being held up by heavy scaffolding. So that means we have a system that is heavy, needs extensive scaffolding and foundations for it, is labor intensive, it's expensive, and generally, especially nowadays, most of the times, it's probably only used once and then disposed of, which means that it generates a lot of waste. So That's important because if we look at standard construction, formwork makes up about half the cost. It's not little. And if we start looking at doubly curved custom constructions, that raises up to 80% or more of the structure's cost, and the material is really a large part of it. And that's not saying nothing because these structures are already 3 times as expensive as the standard one anyway. So it is very clear that we do need to do something about this, to have more efficient ways of building concrete structures. So I'm not the first one to say anything about this. There are plenty of formwork solutions out there, and they have been, and people have tried both in industry and academia to come up with better solutions. Some of them.
It's a real treat to be here today.
Some of them.
This is such a different
cutting
conference.
Alternative materials or improving the speed. Others really look at the reusability of the mold, so that you have adaptive ones. 3D printing, that is also very great because you can really almost make any shape that you want. So there's a lot of that. And of course, some have looked at eliminating the formwork altogether by having stay-in-place formwork that in some cases also acts as reinforcement. These are all great solutions, but they only tackle some of the points great and not the problem as a whole. And a different type of approach to formwork, which again is not new, would be to use flexible formworks, and that tackles these problems more holistically. So again, there are quite a few solutions. In these types of scenarios, though, what you have is usually a membrane that is somehow tensioned or stretched in order to produce the shape of the concrete, and that could be by draping or hanging. It could be through inflation. It could be by supporting the membrane or textile with cables or splines or other kinds of deployable systems, or you could simply tension it in a wooden, timber, or whatever other kind of external frame. So there are some advantages to going away from the traditional rigid formwork into a sort of flexible formwork system. Some of the advantages are the fact that we can get rid of the heavy molds, and we have a much lighter one. That means that you don't need all of the support from underneath. You externalize that a little bit. That means that you have lighter foundations as well. But of course, this does not come without its limitations. So a limitation of this kind of flexible formwork system is that you cannot build whatever geometry. So if the traditional rigid formwork is brute force, you can build whatever you want. You can't do the same with a flexible formwork system. You need to really have a form-found geometry that is kind of different. So I would say that whatever is a sort of limitation is actually an advantage in disguise, because if we want to really be smarter about how we build and take advantage of these things in the formwork, it kind of forces us to also design better structures that use less material in themselves. So at the moment, the types of fabrics that are used in these kind of systems are usually woven-based, so woven fabrics. That mean they're usually flat sheet, meaning that you need to cut and sew them together to create the geometry that you want. They are single-layered, which means that if you want to do anything that is more than just one layer, you need to stitch several pieces together. And because it's a woven textile, it has certain directional properties, so it has a 90-degree angle to it. What does this mean? All right, if we want to make a really doubly curved geometry out of flat sheet material, it means that we need to have developable surfaces, or the more complex our geometry is, the more patches we need to approximate this. All of these need to be stitched together, so that's one part of the stitching, but because it's single layer, you might want to have some channels, some reinforcements, some other things in there, so you'd need to have several layers stitched together. And that's where knitting, which is actually what the title of this was, gives us an opportunity. It's a different type of textile method. So you have weaving, you have knitting, you have a few other ones. And knitting has the advantage of being able to create 3D shapes without needing to stitch things together. So you can create the 3D shape directly. That's a reproduction of the same topology kind of surface, but then in one single manufacturing process. What it also allows for is, of course, wanting to have more, because we don't want to just have flat sheets and one single layer. You want to integrate functionality. You want to have maybe cavities. You have structures that have an actual depth. So you would like to be able to do these kind of things, and that's where knitting also gives an opportunity. Why? Because it can create, yes, full 3D shaping. You can have shaped tubes, you can have branching structures, you can have channels, pockets, openings, and all of that. You might be very familiar with it from your shoes that have all of these kind of features integrated into them. What is also very interesting, and you are also familiar with, is kind of what you see here on the bottom corner. And that's probably something that we're all familiar with in the sense that you've seen it everywhere, you've seen your grandmothers make these, but it means that you can have the material exactly where you want it. So you can have different densities and you can have those aligned to what you want them to be. Now, it sounds like I'm selling knitting quite a lot. It's not so much because you wouldn't be able to do a spacer fabric with a woven textile. You can. It's more the fact that you can do all of these things with full 3D shaping that is interesting for us. So given these kind of things, the objective would be to have a feasible, efficient, economical, and stay-in-place knitted mold. And how would that work? So you'd start from a design, and then you'd need to fabricate a textile using a knitting machine, for example. Then that textile needs to be tensioned somehow to be brought into shape. It would be coated with a special cement paste, and that creates your formwork. That means that we've got two sides to the story. One, you need to get from the design to the knitting. To do this, you'd need to also look into, well, what are manageable pieces of your design, because your design might be quite big. And then for each one of those pieces, create a so-called knitting pattern, which is what you need to fabricate your textile, and feed that to a machine. Now, once you've had the textile, we need to figure out a way to go from the knitting to the actual formwork. And this could be approached in two different ways. So on the one hand, you could transport the textile to the work site because it is compact and lightweight. There, it can be tensioned in the rig in whatever it is supposed to be tensioned with, coated, and then that makes your formwork for concrete later. Or you could do this in a more controlled environment where you take each one of the components, tension it, coat it. You have these very lightweight components that you can then again transport to the work site, assemble the formwork, and whichever way you choose, what you can do at the end is use this for a concrete structure. So let's take a look at knitting, because that's what makes it possible. Knitting, weft knitting specifically, because there are a few others, is the interlocking of a thread to create loops in a course-by-course manner, so in rows. And the unit of a knit is this loop, and it's what makes it possible to create the geometry. It has a certain width, and it has a certain height, which already is suggestive of the fact that you could approximate a knitted textile as a sort of matrix of rows and columns made out of loops. So that's something like this. Now, if you want to create a contoured textile or have shaping, which is what we wanted before, all you need to do is start adding these kind of units from course to course, and to create something like this, for example. So those are also operations that can be done. Some of them are increases, so for example, adding one. Another operation would be decreases, so removing or combining loops so that you get your contour. But we're still left for the moment with a 2D piece of textile, just a contoured one. So what happens when we want to have a 3D geometry, say something bumpy, kind of like this? What you notice is that even though the matrix, so whatever describes the footprint of this thing, is identical to the one before, the length of the backside and the length of the front are not identical, meaning that we need to find a way to include some of these extra features or extra units somewhere in the middle in order to get our bump or our 3D geometry. And those things are called short rows, and it's really the local placement of extra material to get this geometry. This is the trick, let's say, that allows you to create 3D geometry without needing to cut and stitch pieces together, because otherwise you'd need to make that cut and put it together. So once you have a pattern or you have these kind of things, these textiles are produced using an industrial knitting machine. Industrial knitting machines, very briefly, have an array of needles that pull a thread that is brought by this yarn guide to make those loops. And it doesn't have only one array of needles, but it has two arrays of needles facing each other. And that's how it works. And you can switch from which side you do things. So you can do something on the front, you can do something on the other side, you can switch between front and back, or you can do it you can knit at the same time on front and back and then create a connection between the two. And this is what makes it possible to create all of these features and geometries that I've been talking about. So to do this, the machine needs an instruction, so a knitting pattern. Knitting patterns are usually something of a matrix, so they look like this. They're a pixel diagram where every row is a course, so is one pass of this machine, and every single pixel in there is the functioning of a needle, so it's one needle doing something. So if we look at these, an example of such a pattern, what you see is that in some places you don't have needles doing anything, and that's where you have a short row, so these guys would start getting combined to create your geometry. The different colors represent different operations that those needles can do, and we're left with how do you make one of these patterns. So what happens at the moment is you have very skilled technicians that know how to use the software, that click almost pixel by pixel every single place on the pattern. That's not completely true. There are some macros for things that you know, so for clothes or for things that they are usually used for. But you do need the skill of knowing where to place these artifacts to get the geometry that you want. And it might take you a week to do it, but if you then produce 700,000 of them, you don't care. And when it comes to primitives, which are the ones that we usually use, so spheres or shaped tubes, it's very easy to think of where these kind of artifacts need to be placed. But if we start looking at a more architectural scale, so something bigger, and not only something bigger, but also something that is not necessarily based on any primitives, and you could have non-developable surfaces, it becomes a lot harder to imagine what the pattern for this would look like. Not to mention that I don't want to click all of the pixels that would make up the pattern for this, because it's an order of magnitude bigger than anything else. So the challenge there is really to go from a 3D model to an actual knitted object, and for that is to create a knitting pattern in an automated way, and this is one part of the research that I was doing. So very briefly, because it doesn't need to go into detail, how you do this is first by splitting your geometry. It's a choice into smaller patches. How many patches that is, or how is purely up to the person who's making this or the scale of the object itself, and it could be automated. It's not at the moment. The first thing you do is create all of the courses, which are all of the passes of the machine. Within all those courses, find the positioning of all the loops that you have and the relationship to each other, and then translate that to a 2D diagram. This kind of topology is created directly onto the 3D geometry to be translated. So very briefly, if we look at a very small section of it, you have to choose a loop dimension, so what's the width and the height of the loop that you're using, and a knitting direction. Those are the basic parameters that you need. And then in a first pass, we want to create all of the passes of the machine, but because that piece of geometry is not a flat piece of geometry, it means that not all of the passes can go all the way through, and that's what you see here, that some of these passes, oh, sorry, that went through, that some of these passes are so-called short rows, so the ones that don't go all of the way through. Within each one of these passes, what we then do is look at how all of the loops need to be laid out. So we look at the loop width, and we decide what all of these are per course. But what you also notice is that in the other direction, you also don't have all of the going all the way through. So you have these artifacts, which are these triangles that represent either the start of or end of a short row, or in the other direction, they represent those increases so that you go out, or the decreases that you start combining in. So these three steps really make it possible to create the 2D pattern. So, of course, if we have a way to go from a 3D geometry to an actually physically knit object, what you want to do is go to your formwork. So first things first, what do? You get a machine, a hobbyist machine. That's the first thing I worked on, which is a little bit of a manual one, and you try out a whole lot of things. Some nodes, coat it, it becomes really lightweight, very easy to handle. Some rib stiffeners, because we do have these kind of configurations all the time in construction. And this was also created as one textile, right? One process. That's what I'm getting at. And then eventually you make a small bridge and you're very happy about it. But what all of these things do is convince your bosses to buy a better machine. And then really test this at a different scale. So we got a better machine, an industrial one that didn't require me to do things manually, and it allowed us to really test how this would work at an architectural scale. And we did that last year with a Knit Candela prototype, which was a collaboration with Zaha Hadid Architects Code Group. And it was designed for their first exhibition in Mexico City. The shell, which is a homage to the famous shell builder Felix Candela, as the name also suggests, is about 6 by 6 meters in plan, about 4 meters tall, and it has a surface area of 50 square meters. It weighs 5 tons, and it was constructed using 30 kilos of a cable net that was tensioned into a rig, and 25 kilos of a knitted shuttering, so the knitted textile that went on top. So what is special about this shell is not only the double curved geometry, but the fact that it's a waffle shell, meaning that it's a thin shell with stiffeners in 2 directions, with rib stiffeners in 2 directions, so you then have these cavities inside. To do this, to make this kind of shell, what we did was we built a frame, a timber and steel frame. We then tensioned a textile and cable net in that timber frame. But what is interesting here is that you have the textile that has channels and pockets to guide the cable net on the one hand and some inflatables on the other hand. With that tensioned inside, we inflated these balloons that we had inserted into the textile. We coated it with a very special thin, fast-setting cement paste. And then on top of that, cast concrete normally. So this is normal concrete casting. Once the concrete is hardened, you can remove the frame and deflate the balloons, or wait for them to deflate. And you're left with a structure that has cavities, making it a little bit more lightweight, and a textile that is left in place. So this thing that you see here, this little blue line, is also what you see on the inside of the pavilion itself, meaning that you have a textile that fulfills 2 functions this time. One is an aesthetic one, and one is a technical one. So the aesthetic is quite clear, but the technical part is to see that the backside of the textile, which was again produced in one single process, was to have channels for guiding the cables and these pockets and openings. I'm not sure how easy it is to see actually here. Pockets and openings for the inflatables and controlling this. So if we have a look at the front and the back of the textile, you see that they're very different. One of them is quite tight and dense, and you only have a hint of what's going on behind. And the back face, you can see all of the channels, openings for the nodes, and the fact that it's a little bit more loose, meaning that we wanted to make sure that the inflation happens to one side and not to the other side. And this, again, is in one process, right? They're not several things stitched together. They're all in one process. Of course, there are some stitches, because 50 square meters are quite a lot. We wanted to take advantage of the fact that a knitting machine has a certain width, and that's your limitation, the width. But it's a giant plotter, so you can go infinitely long. So we split the geometry into 4 parts, 4 very long strips of 16 to 20 meters, which meant that in the end we only had 4 seams on the whole structure itself. We generated patterns in an automated way, so the way I explained before. This is just a sample of one of the patterns, actually a 1/6 of the patterns. Here, because otherwise they don't really fit on screen. And if we have a closer look at what that pattern looks like, we can really see the relationship between the pattern and the textile itself. So for example, this is what a horizontal channel looks like. That's what a vertical channel looks like. That right there is what creates the openings. And the reason for this is because you have functions. So all of the little colored pixels over there say tell the machine what to do at that particular spot. And those things can be knitting using 2 threads at the same time on one side and the other. It could be reversed, so you can flip which thread goes on in the front and which one goes in the back. You could do only the front and nothing on the back. And there are quite a few other ones. You can knit and transfer, and there are plenty of them. There is enough that can be done. This is just some examples. And if we have a look at what happens when you combine these functions together, you start to understand how these features are created. So for example here, just by combining the different functions, you see that the 2 faces are created, and you see there what it looks like a channel or a pocket. So you can see the fact that they switch from front to back, creating this interlocking. What you can also notice is that you can have a different density on the one side and another density on the other side. So you can really tailor the material properties on a course-by-course basis. All right, so with that in mind, here's the whole process. We knit the textile on the knitting machine. It's arguably the world's largest scarf. It weighed 25 kilos altogether, so all of the 4 pieces. We packed them up in vacuum bags and put them in our suitcases, flew them to Mexico in luggage, because of course we finished this the night before we needed to go to Mexico, right? This is how this works. In the meantime, there was the frame was being built on site, and we arrived, unfolded everything, stitched it all together. It was probably the first seamstress on a construction site that we ever had. It took her about half an hour to create one of these seams. And then with the textile all assembled and snaking out onto the museum corridors, we started putting in the cables, finding the nodes, connecting the nodes, so the intersections between the cables. And with all of that put in, we went outside, put it around the midsection, so the mid-pole of the frame, and hoisted it up because it needs to be tensioned. So we carefully hoisted it up with ropes. Again, it's not that heavy, so it's just 55 kilos, but we were being very careful. We used turnbuckles to tension the cable net. So the cable net is the main load-bearing structure in this case. And we could finally breathe, take a breath of relief that this thing actually stretched to what it was supposed to stretch to. And we got a glimpse of the lightness and the transparency of the formwork that was created. So with this there, it's not only that it created, that the textile was created for aesthetic reasons. Again, the types of features that could be designed with it were such that you can create a very crisp edge and know where you should stop concreting, so at which height your concrete should stop. And then we had, well, Mexican construction workers help us because it is a construction site. And we inserted all of the balloons. They were clown balloons, all of the same size, and we had a lot of fun putting all of these clown balloons in all of the different pockets in very improvised ways. And there were not few of them. There were 1,000 of them. But it didn't take as long as it sounds. It only took about a day to do this. With all of the balloons inserted and inflated and in position, we coated this with a thin cement paste. Lex, he's the concrete magician that is also a researcher and that I work with very closely. And once coated, what we're left with is a Swiss chocolate that looks something like this. And what is interesting here is to remind you that these are the balloons, are the pockets that create the cavities in the final structure. So what is filled in between are the ribs. But what I find more interesting is that usually in a sort of digital fabrication context, in all of this customization, what we do is we say the machine doesn't care what it creates, so it could do 1,000,000 times the same thing, or it could do 1,000,000 times a different thing. And that is correct. And then what we are left with is a nightmare of logistics where every part is labeled and where we need to make sure that every single thing goes into the right place. And that's not the case here, because that intelligence and that logistics is integrated within the textile. They are all different sizes, right? All of those pockets are different sizes, but we had 1,000 of the same balloons. So we didn't need to worry if we are putting the right balloon into the right pocket. It was always the same balloon and always a different pocket, and it was the textile that made sure that it got inflated into the shape that we wanted. And it's the same for inserting the cables themselves and finding the nodes. So finally, with all of that, we had a new type of canvas that, that could be concreted onto, and they really enjoyed it. So we have, the reason this is really beautiful is because you have, so when we say Mexican construction workers, that's really with the utmost respect, because they are really, really good at this, right? They are very good at concrete. They really know how to do this. They know how to create really beautiful finishes. So having them work with this and having a new canvas is really actually an honor. It wouldn't have worked otherwise, right? So this is the concrete being applied to the shell, and then I'd show you a small video of the finished thing, and you can see how smooth the surface is, so what a beautiful job they did at this. And you really work with the local crafts in the sense that you let them do what they're really good at, but on a different canvas. What's not visible here is that the inside is actually soft. So if you push into it, the cavities are behind. The textile is still soft. And sometimes when the sun shines through from a specific angle, you can see the balloon skeletons behind. So that brings me kind of to the conclusion of it. And I wanted to leave you with with just a few takeaways from this project. Excluding the timber frame, which we hope in the future could be something that is deployable or made based on standard elements that could be reused for each project. The cable net and textile costs 2,500 francs for 50 square meters. I think that's about 2,000 British pounds, I'm not sure, of the conversion, but I'll say that. The textile weighed only 25 kilos in total. With the cable net, that's 55 kilos, so still very light for 50 square meters. It took 36 hours to produce on the machine. 36 hours of work versus 750 hours is what you would need to mill the same surface area in foam. And the whole project took from the first meeting, so from the first design meeting to the shell standing there, 3.5 months. And that is incredibly fast, but why this is really impressive is that with other systems it wouldn't have worked as easily. It really streamlines it. The 750 hours that I mentioned before are equivalent to 93 days of work. It would have taken 3 months to just make the formwork for this project alone. So it has some advantages. I'll list them there. Some of the nice ones are the fact that they're lightweight. It simplifies logistics. It's a bit more economic, and it's minimal waste. And the final image that I wanted to leave you with is kind of a vision one. This is a factory. It's not a render. This is an actual factory. Those are all knitting machines as far as the eye can see. So it's a technology that exists, that is usable, that can do this right now very easily, reliably, and cheaply. We use it all the time. It is everywhere. It's ubiquitous all over the planet. So actually, the whole story of transporting this thing from here to there, as light as it may be, I think we could also just send the data and have it produced exactly where it needs to be. So with that, thank you.
Have we got a question for Mariana before we break for lunch, please?
Okay. Is it working? Yes.
Super quick question. What's the yarn you use?
In this particular case, it's PES, so it's a polyester fiber. It's something that is very common, but you can use. So the reason for that is because it is a temporary pavilion. The PES itself is alkali resistant, so we liked that for the concrete work, and it was UV resistant. So because it is exposed, we didn't want the sun to damage it. In general, you can use whatever thread can be used on the machine. So we've done tests with more technical types of fibers, including aramid. The node that you saw before was in aramid just for tests. What you cannot do, so it depends on the specifics of the knitting process and the yarn itself. So anything that can pass through the machine can be used. Carbon, for example, carbon fiber would not be very good suitable because it breaks since it's being pulled by needles. But there are plenty of materials. They could be sustainable ones, they could be technical ones, whatever you might need for a project.
Okay.
Mariana, thank you so much.
Thank you.